You hear an awful lot of talk about hydrogen in steel welds, and so we devised this demonstration to show you hydrogen gas actually coming out of a weld at room temperature. So what I'm going to do is I'm going to take this piece of material here and I'm going to make a weld on its surface, just a bead with a cellulosic electrode. This is a 4311 or 6011 electrode, cellulosic coating, and its coating system is designed to give you quite a lot of hydrogen in the arc environment. And what that's going to be doing is that's going to be cleaning the metal. But unfortunately what will happen is a large amount of that hydrogen is going to be left in the weld. And of course that can create problems later. So what I'm going to do is I'm going to make this weld with this rod. I'm going to quench this piece of material in the bucket of cold water. That's going to shrink the material down, trapping the gas in. Then I'm going to clean it off and dry it up, and I'm going to put it in this beaker of mineral oil. And this is just a clear light oil that will allow you to see the bubbles of hydrogen coming out of the weld at room temperature. Okay, I'm going to take this piece of material and I'm going to quench it in the cold water to lock the hydrogen into the metal. Just going to dry it off now because the bubbles of hydrogen gas tend to stick to the piece if it's wet. You have to remove the slags as well. Yeah, now if you focus in on this piece has just been dropped into the oil. If you look very closely, you will start to begin to see a few bubbles of gas starting to rise out of that small weld bead that's been put on the surface of that plate. Now, some people have said that the bubbles that are coming off of here are actually water bubbles that have been left on the piece from when I quenched it. But of course, since this is oil, if it was water on there, it wouldn't rise, it would sink to the bottom because oil is lighter than water. So there are bubbles of hydrogen gas coming out of that weld. And you can just begin to see them coming out now. We devised this demonstration to show the differences between the amount of hydrogen that evolves from different types of weld metals. Now this particular type that we're going to try now is called a basic type coating, or most commonly referred to as low hydrogen. It doesn't mean that it's simple, it's chemically basic. And chemically basic means that in the arc atmosphere there'll be quite a small amount of hydrogen present. And this is its goal, to keep that hydrogen out of the weld metal while still producing sound metal, doing its cleaning. So what we're going to do is now we're going to make a weld bead on the surface of this piece of plate using a 2.4 millimeter diameter low hydrogen electrode. We're going to quench it into some cold water and then dry it off, chip the slag off of it, and immerse it in this beaker of light oil. And you'll be able to see that there will be very little, if any, gas at all that comes out of that bead. I'm just going to dry the piece off, because if there were any hydrogen gas bubbles on here, they would tend to stick onto that water. So just clean this off. And again, we'll immerse this sample of a low hydrogen bead into the mineral oil. There's no gas, or very little gas comes off of this. There is hydrogen gas that comes off of it, but such a smaller amount. So the rate or the amount that comes off is quite a bit smaller because of using a different type of chemical fluxing. When comparing different types of welding methods as to the amount of hydrogen that's absorbed by that liquid metal, we can then look at other processes. Gas metal arc welding, for example, which uses a clean solid wire with a gas whose moisture content is very low, the possible sources of hydrogen suddenly drop tremendously, and the amount of hydrogen that comes out of the weld is quite small as well. So if we do the same demonstration again, using the gas metal arc process, I'm going to make a small bead on this piece of metal. I'm going to quench it into cold water to shrink the material down, and if there is any hydrogen in there, it will be trapped. And then I'm going to clean it off, dry it. I'll put it into this beaker of a clear light oil, and then you can see that there won't be any hydrogen bubbles coming out of it. If we try this test of capturing the hydrogen that's produced by the gas metal arc process, we can see that there's no bubbles coming out of this weld deposit at all. In fact, there is some, but there's such a small amount that comes out that we're really not even seeing it. If we compare the three methods of shielded metal arc welding using a cellulosic electrode to shielded metal arc welding using a basic coated electrode or low hydrogen, and then to a different process such as gas metal arc welding, we can see that there's quite a large difference in the amount of hydrogen that's absorbed by that steel weld metal. If we're using a cellulosic covered electrode, this amount, this volume of weld metal, this amount, about 100 grams of steel, will absorb about 25 milliliters of hydrogen gas. If you were to trap it all, you'd find that this was about how much you'd caught over about a 3-day period. If we change electrodes to a basic low hydrogen electrode that's been handled correctly, that is, that it's been left in its hermetically sealed packaging, or has been kept in heated storage at above 120 degrees Celsius, we find that the amount of hydrogen that would have come out of this much weld metal will be something less than 10 milliliters for every 100 grams of weld metal that's produced. If we then change processes to gas metal arc welding, we'll find that because we're not using a flux now, we use a dry, clean solid wire electrode and a dry gas, so that there's very little source of potential hydrogen, that the amount of hydrogen that would actually be absorbed will be quite small. In fact, perhaps only a very small amount, and will even be dependent upon the humidity in the welding shop that day. But the difference is that it is quite low. Now, most codes and standards will set limits on the amount of hydrogen that can be absorbed by the metal based upon its service environment, the material type, and material strength. So in many cases we find that when we're trying to engineer a welding procedure that we need to define how much hydrogen we'll have as a maximum. 15 milliliters per 100 grams of deposited metal, 10 milliliters per 100 grams of deposited metal, 5 milligrams, and so forth, depending on the criticality and the strength of the material that's being used.